Okay, welcome back from the break, everyone. We're going to start now to turn our attention to lunar science. That was just a short video from the Dragonfly mission. Again, the half-scale model is out there. Be sure to check it out. But those images, looks like science fiction. It's going to become reality in just a few years. So I'm really excited about that mission. But let's now talk about the moon. This session is actually brought to us by Lockheed Martin. You can see it on the easel over there. Thank you very much for the sponsorship. We want to give a warm introduction to our moderator, Joel Kearns. He's the Deputy Associate Administrator for Exploration downtown at NASA's SMD. Dr. Kearns manages the Lunar Discovery and Exploration Program, also known as LDEP, along with the Commercial Lunar Payload Services, the CLIPS program. He held prominent positions at Glenn Research, out at Ames, down at Marshall, at headquarters. He's pretty much been all over the agency doing good work. And Joel also earned his PhD from Worcester Polytechnic Institute in Materials Science and Engineering. So with that, Joel, over to you.
Thank you. This is an exciting time to be working on lunar science, both in the United States and internationally. So I think you're going to hear from this panel why we think so, and also we're looking forward to getting your questions. Let me introduce the panel members that we have today. To my right, we have Dr. Rachel Klima, who's a planetary geologist at the Johns Hopkins University Applied Physics Lab. Her research focuses on developing techniques to extract quantitative mineralogical information, as well as information about weather and other volatiles from remotely measured spectra of airless bodies in the solar system. She's also the director of the Lunar Surface Innovation Consortium from NASA Space Technology Mission Directorate, which is used to promote innovation and conversation among members of the public and the private sector who are all working on building a sustained presence on the lunar surface. She's also currently the deputy PI of the Lunar Trailblazer mission, which will launch, looks like the end of this year. And she's an instrument scientist of the Lunar Vertex instrument suite, which will land in 2024 and explore magnetic anomalies and swirls around Reiner Gamma. To Rachel's right is Dr. Philip Metzger. He's a planetary scientist at the University of Central Florida. Before that, he was with NASA for almost 30 years, working on the Space Shuttle, the International Space Station, and also developing technology for planetary surfaces. He focuses his work on lunar mining, resource extraction, surface construction, and physics of rock exhaust blowing across lunar soil. I guess it's plume surface interactions, right? And he's currently modeling how lunar volatiles be measured during the NASA Prime 1 payloads mission on the moon. Again, that will be the end of this year, and supporting several companies analyzing how the lander's exhaust will affect the lunar landing zones. And to the far side of the panel is Dr. Ryan Watkins. She is a program scientist with the Exploration Science Strategy and Integration Office at NASA's Science Mission Directorate in NASA headquarters. She manages and oversees programs within the Lunar Discovery and Exploration Program, including PRISM instrument development, CLIPS landings, Artemis human landing system deployed instruments, and her expertise is in understanding the effects, again, of rocket exhaust on the lunar soil, physical and compositional properties of the lunar surface using remote sensing data. Let me say a few words as moderator about why this is an exciting time. So think back more than 10 years. In 2009, Lunar Reconnaissance Orbiter entered orbit around the moon. It's been sending back measurements and images since. In the mid-2010s, the decision was made to go forward and construct an outpost around the moon for humans to visit, which would be known as Gateway. And it was discussed in one of the earlier sessions on space weather, how Gateway will host instruments for space weather, such as the Hermes instruments. In 2017, Space Policy Directive 1 was issued from that administration, which said that human spaceflight would have a focus related to cislunar space and the lunar surface. In 2018, NASA, with the agreement of the administration and Congress, established the Lunar Discovery and Exploration Program, and as a key tenet of it, implemented commercial lunar payload services, that is, buying the service of getting instruments and cargo to the moon as the way that the lunar science and related activities of the lunar surface would be conducted, which was a big change compared to standard ways that NASA would do business. In 2019, the National Space Council for the White House set NASA on the course of having astronauts visit the south pole of the moon for the next human exploration. That is currently scheduled to take place, the very first landing mission, the end of 2025. More recently, the space tech at NASA has worked with industry to put the Capstone position navigation and timing satellite in 2022 into the same near rectilinear halo orbit that a Gateway will use as its orbit. And of course, the end of 2022, you also heard the successful test flight of Artemis 1, which tested the Orion human spacecraft, the Space Launch System rocket, exploration ground system, ground infrastructure, that'll be used in 2024 to send people in orbit as a flyby around the moon. But there's a lot more things than that that are going on. You know that Artemis 1 deployed several CubeSats, including the Lunar CubeSat, to do measurements around the moon. iSpace Japan launched their Hakuda R Mission 1 lander at the end of 2022. That's currently in transit to get to the moon. They projected to land in April. And as well on that mission also, as a rideshare, NASA launched the Lunar Flashlight investigation to go to the moon. Today, there are 7 CLIPS awards that NASA has made to bring scientific instruments or other cargo to the surface of the moon and return data. NASA has also selected 3 more investigations and suites of instruments for 3 additional CLIPS missions as of today. And also we're working on selecting instruments for missions to follow that today. We also have an open competition going on today to pick the scientists who will guide astronaut geometry on the lunar surface on the first Artemis mission. So as you imagine, just from that, there's an incredible amount going on. In addition to that, we received updated recommendations from the National Academy of Science for astrophysics in 2020, in the end of 2021, and then in planetary science and astrobiology in 2022. And NASA, on top of that, spent quite a bit of time last year based on all that recommendations and where we are today to map out scientific and other objectives for NASA's work, which we refer to as Moon to Mars, or you could think of as Moon and Mars, how we will have human spaceflight progress further out into the solar system with our partners around the world. So having said all that, I think that'll give you an idea of everything that's going on. What I want to do is first ask our panel members for their view on what is different about space science today in 2023 as compared to the last time it was in the moon was the focus of attention in the world, going back more than 50 years ago to the Apollo human landings. We first go to...
Okay, so I think to me, one of the biggest differences is that we're going to the moon in a much, I shouldn't say more collaborative way, but in a way that allows access for more scientists, more people throughout the entire world, throughout the country, bringing in commercial industry, bringing in international partners, looking at this as a challenge that can really bring people together is very different from the kind of like a Cold War race environment that we went to the moon towards in the first place. The other thing is that we're kind of expanding our sphere of a scientific laboratory in some ways, like the Lunar Vertex mission that I'm an instrument scientist on is using this magnetic anomaly to not only understand how that formed, but as a natural laboratory for understanding space weathering throughout the solar system. So we have this really unique opportunity through the continued CLIPS landings, through the human exploration, through Artemis, through this greater access to basically have this new wonderland of where we can start to test some of the things that that we think we understand, that we've learned from planetary science, from even Earth science over the last 50 years. So I'll let Phil go next and then save my other stuff.
So I want to just talk for a moment about the big picture. What are we going to get by going back to the moon? Sometimes people will object, we've already been to the moon. Why do you need to do this again? And my answer is, well, we went to the moon, we brought back a lot of material, and that enabled us to formulate the questions that we really need to go back to get answered. And some of these questions touch on the biggest, most important science questions that there are, bar none. For example, is there life elsewhere in the cosmos? Are we alone? How far away do we think we might need to look to find another life support planet? Now, you might think, why do we go to the moon to study that? Because the moon is an airless, lifeless, kind of a dead rock. And that's exactly why we want to go back there. Because here on the Earth, with plate tectonics, and we've got the atmosphere and the hydrology, it's constantly erasing the geological data. And so trying to look back in history to the early formation processes of our planet and of our solar system, that can only take us so far. But lunar scientists like to say the moon is Earth's attic. It's where we go to find the family history that has been stored. We have to go up to the attic to get those relics and study them and find out about our past. So, for example, there was a meeting a few years ago in Nice, France, where some astronomers put together a model they call the Nice model, which says that the solar system was probably disrupted about 3 point something billion years ago. And because Jupiter and Saturn got into resonance, and Jupiter kicked Saturn, and Saturn kicked Neptune, and Neptune plunged into the Kuiper Belt and scattered the Kuiper Belt, pushed it out about 10 astronomical units, and about 10% of it may have come in and bombarded the Earth. And this might be the explanation for how the Earth got water, and where the carbon that forms our bodies, how that got back to the Earth, because a forming star will push away those volatile elements. So how did they get back here? Well, the way to find out, did that really happen, is to go to the moon and dig trenches and study the impact ejecta blankets, how they become finer and thinner over distance, so that we can date all of the layers of impact ejecta blankets and create a really highly reliable, calibrated model of the impact history of the inner solar system, and then date when a disruption occurred, so that then that can constrain the planetary dynamics models, and that will constrain our understanding of how probable is it to get an Earth-like planet with water, oceans, and carbon-based life forms elsewhere in the cosmos. So these kinds of big questions can only be answered if we can go to an airless body that doesn't have too much active geology anymore. Unfortunately, there's one that's just right there, the next planet over, secondary planet. And so it's going to be a really exciting time once we get back to the moon, get this data, and begin telling the public the amazing things we've learned.
Yeah, just to build a little bit off kind of what Rachel said initially, I think one big difference between now and back when we went to the moon with Apollo is the commercial aspect. We have a lot more commercial partnerships now, not only with the Commercial Lunar Payload Services Program, or CLPS, that's enabling scientific investigations across the surface of the moon, addressing high priority science questions like some of the ones that Phil mentioned. But we're also partnering with commercial companies for Artemis. It's NASA's not building the human lander this time. So we're partnering with SpaceX, and then later another company to actually land our humans on the surface of the moon. We've got, commercial companies building the spacesuits. So there's a lot more, kind of commercial partnerships in that sense. That's a big difference. Also, we're going to stay, which is a little bit different than Apollo as well. We're ultimately working up towards a base camp, and how can we enable a sustained presence on the lunar surface. And again, like Phil said, we've got a lot more science questions we're trying to answer now. We're sending humans to the South Polar region of the moon. There's a lot we don't understand about volatiles and just the environment in the South Polar region. And again, with CLPS, we're going to the swirl that Rachel mentioned to learn more about space weathering. We're sending a delivery to an interesting volcanic construct that's different than anything else we see on the moon. So yeah, just a lot of different science priorities that we're trying to work off of as well. And then I think another big one too is just the diversity of people working on the program. You've got people from not only a variety of demographics, but background experiences are coming from different fields, different walks of life. You've got early career scientists are just as involved as the more senior scientists. So I think that's another big difference as well in the Lunar program today.
Thank you. It's interesting to talk about the international components, particularly when we send human explorers to the moon. A major element of the Orion spacecraft is the service module is actually made by the European Space Agency for NASA. And there are many international contributions to the Gateway that will be being pulled together from Japan, from Europe, from Canada, other organizations. And of course, there are many internationally led robotic missions coming up to the moon. People are working actively that I didn't mention in my introduction. There are missions from India, from Japan, a mission from the Russian Federation. There's a great deal of work that's been done by the People's Republic of China over the past few years, which will continue into the future. Let me ask you about something else which may be a little different from the Apollo era to today, and that is since Apollo 50 years ago, NASA has sent teleoperated robotic explorers throughout the solar system. We have advanced instrumentation and rovers on Mars. We have very high productivity and high resolution instruments probing the planets throughout the solar system. So now when we have more of an emphasis on robotic investigations on the moon, but we're about to have human explorers also go back starting at the end of 2025 starting at a very particular place, the South Pole of the moon. How do you think we, meaning the world and the United States, will be using robots and humans on site maybe differently than we thought of using them 50 years ago, or differently where we've had robotic explorers the last few decades?
Well, I think that's one of the big paradigm changers, the ability to use robotics more efficiently. People are always saying, well, should we do humans in space or robots in space? And the only right answer is both. Humans are going to be much more efficient when we have robots doing a lot of the tasks that don't require human attention, but there are certain things that only humans can do. If you put a field geologist on a planetary body, they're going to produce so much science in a short amount of time, much more than you could do with a robotic mission. Not to denigrate the robotic missions, which have been amazing, but humans bring a capability. And furthermore, humans bring a lot more engagement with the public, which helps the funding situation. And so I think it's always going to be both together. Robots will make it more affordable for the humans. Humans will make it more effective with the robots. And with artificial intelligence, making the robots ever more capable, the ability to leverage our presence in space is going to be growing dramatically.
You want to go? Okay. Yeah, I think this partnership between humans and robots also, when there are tasks, for instance, we talk a lot about building infrastructure and setting up, for instance, some VSAT, so vertical solar array towers that would produce energy at the South Pole that would help support a lunar base. There's going to be maintenance that needs to be done. There will be some tasks that can be done autonomously, right? So you don't need to waste the human's time doing some of the maintenance tasks. Of course, there's going to be some things that you can't necessarily do, but we've learned a lot about on-orbit servicing and how to do these things robotically. So there's a lot of work going on with that. That will take away some of that burden so that the precious time we have on the surface can be used for the things where you really need to think on the spot. And the other thing, which is super exciting right now, right, is that we have kind of augmented and virtual reality capabilities that can allow us to be more effective with the robots and also with the astronauts to help engage others on the ground, to engage the public and really help them share that experience. So I think we have, with the technology developments in robotics, AR, VR, autonomy, and all of that, we're going to be able to have a really rich experience that's shared throughout the world much more readily.
Yeah, no, I mean, I agree largely with what my fellow panelists said. I guess just to build on that a bit too, you know, like Phil said, you know, robots and humans, we work really well synergistically. You know, we're looking at things like, which I'm sure will come up again in this panel, the Endurance mission concept, which is going to be a long duration rover to collect samples across the South Aitken Basin of the moon that will later be retrieved by astronauts. And so, yeah, so you get, you know, some of the heavy lifting of the sampling done before the astronauts even get there. And so then they can pick up those samples to bring them back, but then they have their time dedicated to other tasks while they're there. So I think that's one great area where we've got some robots and humans kind of interacting together. We're also discussing, you know, the lunar terrain vehicle that the astronauts will drive around will also be potentially outfitted with science instruments. And then when the astronauts aren't there, then they can, you know, tele-robotically operate it, you know, from Earth or Gateway or wherever it might be. So they can continue to do science while the humans aren't present. So yeah, so I think we're seeing a lot of really neat capabilities emerge here.
You mentioned, Ryan, the Endurance A mission to South Pole Aitken Basin, which was a highly rated recommendation from the Planetary Science and Astrobiology Decadal Survey. Could you add to what Phil said and address what the goals were there for that recommended mission?
Yeah, so like Joel said, this was a recommended mission that came out of our latest Planetary Decadal Survey, which outlines, you know, science priorities and mission priorities for the next decade. So one of our big outstanding science questions about the moon is centered around the South Pole Aitken Basin and the cataclysm hypothesis that Phil mentioned. Like, was there this late heavy bombardment of the moon that may have affected some of these, you know, models and such? And so the South Pole Aitken Basin, it's the largest basin on the moon. It's on the far side. It's also, you know, the oldest and the deepest. And so getting a date for the age of this basin is really critical in constraining the lunar chronology, which is also critical for understanding, you know, the chronology on other planets, because they're anchored on our lunar chronology curve. So that's a really important piece of information there, is to get samples where we can directly date the age of the basin, determine if there was this influx of impactors in early solar system history, as well as, because it's the deepest basin on the moon, did it excavate materials from the mantle or from deeper within the lunar surface? And so getting some of these samples can help us to better inform kind of the materials that they're made up of, you know, the lower crust and upper mantle of the moon as well. And so, yeah, so this mission concept would be a rover that would essentially rove across the basin, get strategic samples from different locations, and then leave those for the astronauts to retrieve.
And one thing that's super exciting about that mission is that, you know, for years we've wanted a sample back, and that meant probably, you know, a robotic lander that would pick up what you can get there and then bring it home. And that would probably answer a lot of the questions we have, but by driving across the basin and getting multiple samples, like we have the potential to answer the age date question, really get at this question of what the lunar mantle is made of. You know, I mean, the moon, I'm going to try not to geek out too much here, but it's not going to work probably. As you know, as a rock geek, understanding how the moon formed has really informed our understanding of how all rocky bodies evolve in the solar system, and the way this magma ocean stage, and what happens once you get this layering. Does it turn over? You know, how do you get that mantle that you see on the Earth? How do you get that mantle that we presume is on the moon? You know, which minerals comprise it? How big do you have to be to make that? Do you know, so many exciting geology questions can be answered. And, you know, by collecting all of these and knowing where we got them exactly, I mean, that's what's been so incredibly powerful about the Apollo samples, is that we have their geologic context. And yeah, they've been flung around, but we can trace it back because we have orbital measurements that we can compare with the laboratory measurements, but they're all like in that one area on the near side. So by having this far side traverse with multiple rocks, like, it's really going to unlock so many questions about planetary formation in our solar system and probably in other solar systems. Sorry, I had to geek out there.
Let me ask you about a different scientific priority topic, again, that was recommended in the Planetary Science and Astrobiology Decadal Survey, and that is understanding volatile cycles on the moon. Could the panel address what does that mean, and how does that relate to information that someday human explorers or commercial concerns might be able to take advantage of?
Well, this is not my main area of work, but I'll say this, I've been in this room 3 times now. The first time was for a meeting on that question. And I remember people were talking about, well, we're pretty darn sure that there's ice at the South Pole of the Moon and the North Pole. And it's probably got complex chemistry, like a lot of carbon, and there's some ammonia and some organic molecules. But there's a lot of discussion at that meeting on where did it come from? And there were, if I recall, 4 main theories. One is that it's created by the solar wind interacting with the surface of the moon. Number 2 is that it's carbonaceous dust, interplanetary dust, raining down on the moon constantly, like a very slow drizzle over geologic timescales. And number 3 was it came out of the core of the moon as it was solidifying, and from this magma ocean stage. And number 4 is that it was larger impactors, comets and asteroids. And it's probably some of all of that, but we need to really figure that out, how much of it is due to each of these processes. And because the geological history of the moon is very complicated, we really need to get there. We need to drill samples from different depths and different locations to put together the whole story on the volatiles in the inner solar system.
Yeah, so one of the missions that I'm working on is going to try from orbit really answer some of those questions. So with Lunar Trailblazer, we're going to be, we have these different hypotheses. So we think from the near infrared data that we have right now that water or hydroxyl is migrating on the surface of the moon. But we have to test that because we haven't made the temporal measurements in a controlled way. So we thought the moon was super dry. First of all, for those that are not familiar with it, based on the samples and the minerals that we see, we were pretty sure that there wasn't going to be a lot of water in the rocks when we got back, when we went with some of these more modern instruments to look at the spectral properties of the moon. But we saw water, which we didn't expect to see it all over the place. We thought we might see it at the poles, based on radar data, based on modeling, based on lunar prospector data where they saw hydrogen. But we really didn't expect to see it in the illuminated regions of the moon. But we did. And so we're like, what's happening? Is it forming so quickly and migrating that we are maintaining it on the lit surface of the moon? What is that modern water cycle that's going on? So how quickly is it formed? How quickly does it move? Or were we maybe just wrong and it's been hanging around? It's from cometary impacts, it's from other things, and maybe the stuff isn't really, because we have samples from a very restricted area, maybe those were just very dry because of the volcanism in the Maria. So getting more orbital data is going to help that a lot, but getting down on the ground, getting more rock samples from different locations, we can detect very small amounts of water with modern technology. The other thing is too, which you mentioned with the cores, one thing that is really like astounding to think about is, think about how much we've learned in Antarctica from ice cores. You take a core in a permanently shadowed region, and now you're sampling back like 4.5 billion years, like with those layers there, and looking at the organics, looking at any isotopic composition of any water that you find there, you can start to get at, is it from comets? Likely. Is it, do we think, does it look like Earth's water? Because if the moon formed from the Earth, the isotopic abundances might be similar in some of those rocks. So there's a lot of really, really cool questions we can get at as far as, the intrinsic water and more recently formed water through the solar wind interactions.
Yeah, I don't think I have anything super more valuable to add than what Rachel just said, because volatiles is also not my area. But I think another interesting thing to look at too is that one aspect of the lunar community is particularly interested in is how can we then use these volatiles to sustain the human presence there. Can we use it for water or other resources? So there's our Viper mission and then some others that are going to be doing, resource prospecting to look at, just where the volatiles are, how much are they, or, what form are they in, and then how can we use those to, support humans while we're on the moon.
Let me add to that. That's a great point, Ryan. And sometimes people object to the idea of using those volatiles as a resource because what if mining it messes up the science? That's an important question, and we do need to manage that. But in general, economic applications in geology have driven science forward much more quickly than purely academic efforts. And that's because when there's an economic application, then you get more funding, right? But we need to...
It's a good motivator.
Yeah, but what we need to do is manage this so that if we start utilizing those resources, the volatiles on the moon, we're collecting data from them at the same time, and then we should be able to get vastly more access to that data by doing that, as well as, like Ryan said, economically making ourselves more capable to do things in space, to go farther and do more.
I think, and that's something that's really important about the way NASA has been functioning over the, my career, basically. It's getting better and better integrated, where there's discussions about how do you make sure that we think now about what we're doing and very intentionally plan in, how are we going to measure these things? How are we going to make sure that we preserve the science while still doing the other things? So not one goal trumping over the others. How do we carefully plan our strategy so that the science is integrated into the exploration, so that the exploration is driving the technology developments, so that the technology developers understand the science that they don't want to mess up because it's going to benefit everyone in the long run. So I think there's much more collaboration across the agency than when I was a grad student, for instance, although I might have not. I was probably naive and didn't know what all was going on at that point, but that's something that's really been impressive to me.
So, Rachel, now we talked about what lunar missions you're working on, but as listed up here, and I mentioned that you're also director of the Lunar Surface Innovation Consortium. Could you talk about that and talk about how that enables or influences lunar science?
Sure. So that's it. I've been doing that for, I guess, since right when COVID started, basically. Like, we had our kickoff meeting and then kind of went home and worked from our homes for quite a while. And it's been really interesting to me, coming from a lunar science background, to take this turn and work with trying to start these dialogues between those in industry that are, their kind of first directive is to ultimately have a profit, right? I mean, they do need to make money off of doing these things. They're not just doing it for the scientific drive. And get them talking together, both with the scientists, with those that are trying to chart this grander course of understanding the moon and how to operate off planet, so that NASA can then go further into the solar system. So, it's been a very interesting journey, basically. So what we've done is we've started to engage members from government, from academia, from industry, so not just NASA, but other government agencies, whether they be in the United States or outside of the United States, and have this ongoing dialogue about what are the things we absolutely need to get to this end state of a sustained presence on the lunar surface. And what drives that, whether it is the science requirements of the things we might like to do there, or other activities that people would like to ultimately do. So there's, of course, people are interested in tourism on the lunar surface. People are interested in what kind of industrial applications, whether it's using the resources for potentially for propellant or for other, off-world refining of materials. So, yeah.
Now, Phil and Ryan, you both when I introduced the panel, I stated that both of you who have worked doing studies in rocket exhaust, right, plume surface interactions. Could you talk about what is still to learn in that field and how it is being applied and how important it is as we start sending more things to the surface of the moon and we are trying to
How
do
much time do we have?
science?
We've worked together on this,
Yeah,
too.
I'll let you start. Bill.
No, you start,
Okay,
please.
there's a lot. There's a lot still left to learn. And it actually kind of ties back into a little bit about the volatile question we just discussed as well. Prior to Apollo, obviously we didn't have a lot of data about what happens when you land on the moon. I mean, there's a little bit from, Surveyor and Luna, but yeah, when you land on the surface of the moon, you blow a lot of dust around. And so, I mean, Phil's been doing this obviously longer than I have, but there's obviously, yes. I was his intern, so I can say things like that. But yeah, so there's a lot we still don't understand about what actually happens, and the physics of the what happens when you land on the moon and the rocket exhaust interacts with the surface, what physical changes occur to the surface, and we didn't really have the dedicated types of measurements during Apollo that we really need to understand this problem. And so now we're looking at obviously going back to the moon. We're looking at going to an entirely new terrain in the South Polar region. We don't know exactly how the temperature differences down there and the volatile differences are going to affect the surface, and then therefore what happens to the surface when you land a rocket. Not only that, but we're landing a much larger lander than we've ever landed before, and so now there's questions about the size and the engine configuration, and so there's a lot of variables that come into play here in order to understand what you're doing to the surface, and then how that may impact nearby assets or your rocket, what kind of damage you may cause. There's also a lot of questions now about the products in the exhaust, and can those now travel to these permanently shadowed regions and then contaminate the very samples that were there to actually try to get and understand. So Bill, I'll let you add to that.
Yeah, so Ryan and I worked on this when I was at NASA many years ago, and at that time we were trying to piece together clues because we really didn't, there was no dedicated instrument. We only had the Apollo videos, and so you're looking out the window, looking down at the ground, trying to figure out, okay, what exactly is happening here? We see the white dust, what is going on there? And you couldn't tell by looking at the videos that dust is going about 2,000 or 3,000 meters per second, which is pretty darn fast, like 6 times a bullet. So one of the clues came from Surveyor 3 spacecraft. We went to Houston and we dug through their box. We didn't dig through it, but we got their box of hardware that was brought back from the moon by the Apollo 12 astronauts. And they went to the Surveyor and they cut pieces off and brought it back. And so we had that in the lab for several years. And one of the things we found out was that the sandblasting from the Apollo did not coat Surveyor 3 with dust, because it was already coated with dust. And that was a new mystery. Like, how did it get coated with dust? But what happened was the Apollo landing resulted in a net removal of dust. It sandblasted it and partially cleaned it, but damaged everything in the process. Crushed the paint surface and penetrated it with little sand grains and cracked it all up and etched things. So we've been working on the mysteries of what exactly is going on, and why do these fluids in vacuum and low gravity, supersonic flow, that it's rarefied, why does it behave this way? So we talk about the moon. We're going to do science on the moon. We're going to do, what are those 3? I'm sorry, I'm blanking now. Science on the moon?
Of the moon, on the moon, and from the moon.
Okay.
Yeah.
One of them is like telescopes on the moon looking out. One is studying the moon itself. One of those 3 is taking advantage of the environment of the moon to study things that you can't study here on the Earth. And so this is one of those things. How does rocket exhaust, or how does supersonic gas expanding into a vacuum behave? We have no models yet that can capture all of that physics, and we have no real data sets to guide those models, because we can't do those experiments on the Earth. How do you blow a supersonic flow into a vacuum chamber while maintaining vacuum and do it inside of a reduced gravity aircraft at the same time? you can't
No
do
big
it.
deal. Yeah.
And especially if you're blowing dust, which is going to ruin all the vacuum pumps. So we really want to get back to the moon and do physics research on the moon to help understand these problems.
Yeah, and I just want to add one more thing too. Like a lot of people think, well, this is an engineering problem, but it's also a science problem. I mean, I mentioned the volatile issue, but it also has implications for when we do send humans back. And if you want to get a sample that you can claim is pristine, you're not going to do it in that blast radius. I mean, we don't excavate very deep into the surface, but you are removing some material. So if you want to get really true pristine samples, you've got to have the capability to get beyond your lander, beyond this blast zone, which is obviously even more important for astronauts who are wanting to go back and sample.
So many of you mentioned different studies in the conversation we've had on the panel. People traditionally think of planetary science studies, but there are highly valuable scientific studies proposed in the National Academy's decadal surveys and other community documents in other fields like astrophysics. You mentioned about telescopes on the moon, in heliophysics, in biological and physical sciences, the laboratory sciences, we mostly associate with low Earth orbit today. So there's a real drive to make the measurements that really produce high quality science, whether it's remote sensing, in situ on the surface, bringing things back to Earth. But at the same time, we're using new paradigms to try to do things faster, reduce the cost. We mentioned the CLIPS initiative that NASA is exercising now. NASA doesn't actually design or own the landers or conduct the missions, the robotic missions that go to the moon. We contract with industry. We tell them what instruments we want them to carry, what data we want back, and then it's up to them to do it as a service for us. And of course, there's also cost constraints. We want to get the maximum science we can for the money that's available. I wanted to ask if you could share observations you've had watching as we implement some of these new paradigms, for example, commercial services and constrained budgets, even as we're trying to move to higher and higher quality science as we get ready to go back en masse to the lunar surface and cislunar space.
So I'll jump the line here a little bit. So I've seen this from a couple different viewpoints now. So so Lunar Trailblazer is a simplex mission. So that's a low cost mission, just around, well, low cost to a tenth the cost of what was previously the lowest cost planetary mission class, and Lunar Vertex, which is more like a 20th the cost. So it's a very different and really exciting mode of operating, because you have to make those questions of like, how can you maximize your science, but you just can't go over in the cost. We need the vendors to come in, and we may have new companies that have great ideas but haven't actually implemented them in space. So it takes a lot of collaboration among the different partners to help mentor them along the way and make sure that they can deliver what they've claimed they could deliver in their designs. And from the other side, for places like even like APL, or like from some of the established companies that have done larger scale planetary missions, trying to learn how to make the cuts you need to stay in that cost constrained environment is a challenge. So you kind of have it coming from both directions. But if we can be successful at this, like the CLIPS program is going to like open crazy doors for us to be able to do lunar science all across the lunar surface. So, while establishing that base camp at the South Pole is going to enable all kinds of things, the access that we have to the moon, to everywhere on the moon through CLIPS, and in this competitive environment, it drives great science. It drives competition among the different providers, and hopefully builds this new economy. It drives technical development and innovations that we can use here on Earth as well. Some of the things that we're doing for thermal control, for power generation, a lot of these things are very useful to us on Earth as well. So I think, going to this new mode that's very different and a broader playing field is really going to open all kinds of amazing doors for us in space science, and just in the country as a whole, and the world. Sorry.
No, I mean, Rachel had a lot of really great points. But yeah, I mean, I think, one of the ones you mentioned is just the access to the lunar surface and the variety of science questions we're able to answer now. Because, even with the Artemis, we're going to one location, and there are a lot of science questions there, but there are a lot of other science questions that you can only address on other locations on the surface of the moon. And so, yeah, we're going to a lunar swirl, we're going to a volcanic construct. We're going to all sorts of different places where with our latest, call for payloads, we open it up as proposers. You get to pick, like, tell us what destination you want to go to and what science you can do there. So really just enabling just so many more scientific investigations. And like you said, enabling.
You get 10 for the price of
Yeah, and
one?
for
That's crazy.
very reduced costs. It's enabling a lot of, international partnerships as well using this commercial model. Just being able to bring in international payloads and fly them on our CLIPS landers as well. So, just again, enabling these companies and the competition. It's just been a big paradigm shift for sure.
It's very full of energy compared to some of the bigger ones where there's so much paperwork and everything else. It's really exciting to be in these quick engineering decisions. All right, that's not working. What do we do? Let's pivot because we got to deliver quick. And we've got to stay on track. So let's make the choices and move
schedule.
on. Yeah, it's neat. It's a great time to be alive.
I guess the only thing I'll add is that I've done some work recently on the economics of spaceflight, and reliability is an exponential function. So the more reliable something is, the cost goes up exponentially. And so if you can work with these companies with a little bit riskier missions, a little bit higher chance that they might fail, but by working with the companies and having lots of missions, you should be able to get, if the models are correct, if the economics models and the engineering models are correct, you should be able to get a lot more science for the money by doing it this way.
So let's turn to see if there are questions here at the auditorium for the panel or any that'll come in from online.
Oh, hello. I have a question, and since many of the talker here, they are used to working in NASA's or also are currently working in NASA's right now. And a lot of people mentioned that during the Cold War, the exploration of the moon was mainly led by the governments. However, in nowadays or in the future, do you think that the private companies like SpaceX or other robot company will get more and more involved in the planetary exploration? And if so, what are some potential ways that those private companies can do in the next 5 years or 10 years?
Should I go? I'll go. We're already seeing companies like SpaceX and Blue Origin putting a lot of internal investments into things that, where they might go further than just doing transportation, so doing some of the exploration. I think there needs to be a driver, right? There has to be some kind of buyer for the things that they would be doing. So I think we need to make sure that the customer base is clear if we want to have that driven from something other than just pure kind of science for the sake of science. But I do think, I think that there are definitely companies that do see a financial future for doing different activities on the moon. So that's definitely going beyond just government agencies.
Yeah, and I guess I just add that, kind of one of the goals of CLIPS has been for NASA to be one of many customers. We're not the only customer, and we are, it is kind of our vision that these companies, SpaceX and the others, will be able to then, do their own missions to the moon, even without NASA as one of the customers. And so, we're already starting to see companies talk about this, and they're developing new technologies, looking at communication satellites and rovers and all sorts of different things that are, independent of just landers that are delivering NASA payloads.
So I have a paper in peer review right now. Hopefully it'll get out of peer review someday, but it talks about the economics of lunar volatiles as rocket fuel. And tried to do the most thorough job I could possibly do, and it really does show that there's an economic business case for making rocket fuel and using it to boost communication satellites from geostationary transfer orbit up to geosynchronous orbit, for example. It can also be used for lowering the cost of doing a Mars campaign, sending humans to Mars. So I think there is a business case for companies that want to get into doing that. But the first business case for companies is always going to be supporting NASA, developing capabilities to do exploration on the moon and on Mars and elsewhere. But then the technologies that are being developed by supporting NASA can get spun into these other commercial applications. After rocket fuel, what's the next commercial application? That's a hard question. Partly because the businesses that have business models won't tell you because it's their intellectual property. But there are a lot of companies working on business models right now for doing things in space.
Well, the other thing too is like as a provider to support some of these other activities, right? So providing power, providing comms, those things are very attractive. And NASA wants to buy a lot of those things, even buy data, like we heard about in the previous panel, as we do on Earth, buy data that's produced in some cases by commercial companies. So we're trying to move forward sort of more together so that there is that business case.
Let's go to the center aisle here.
Yeah, you were talking earlier about the very fast turnarounds with the CLIPS and other smaller missions. One of the problems with them is that they often aren't as resilient, so are very susceptible to delays with launches and things like that. And usually, since they're secondary payloads, often get housed quite far in and are hard to go back out and recharge batteries and check the health of. Is this something that is on the minds of people at headquarters, and are they thinking about changing processes to make it easier for those involved with those science payloads to be able to have access to them and make them ever so slightly less risky?
Well, I'd say that the answer in general is yes. You know, we're always looking at lessons learned, whether it's from the deployment of the CubeSats on Artemis 1, or it's watching how long it's really taken the CLIPS companies to get ready for their first missions. You know, when NASA went to this model, for example, in CLIPS, I think when the original orders were awarded for it, there was hope that those initial missions would fly in 2021, and they're going to fly in the middle of 2023. So we've been looking at that in terms of trying to understand what really drove that and how that might change our planning for the future, or how we might introduce new things into CLIPS or in lunar discovery and exploration. Also, we look at the performance as we drive to smaller and smaller satellites and CubeSats, you know, look at the performance, try to learn from that, what type of technologies need to be developed ahead of time or matured further, and make those available to the proposer community. Yeah. One here. Okay. Let's go.
So you mentioned about robots versus humans as we go into space exploration. So in terms of lunar science, both are useful. Like some tasks humans are more efficient in, but also the other tasks which robots can do, it's better to do in a more autonomous manner. But as we go farther and farther to other planets, to different parts of the solar system, the time of travel with the existing technology of propulsion increases exponentially. So in that scenario, how worth is it to send humans instead of robots for certain tasks?
I'm sorry, the acoustics are kind of bad here, but you said time of travel?
Yeah, so if we go farther and farther into space, for example, Mars and then beyond, it's going to take longer for any sort of spacecraft to reach. So is it worth it to send humans for any sort of explorations in comparison with robots?
Yeah, so I'm going to give you my opinion. My belief is that there is just simply a support in America for humans in space. And if you were to cancel that, the money would not get reappropriated into robotic missions as much as we might want it. So the goal is going to be to use human space exploration for science rather than try to eliminate it and replace it with something else. Now, that's my opinion. But to directly answer your question, the technology or the problems of taking our biological bodies out into space where we're not adapted, these things can be solved with technology. Bigger spacecraft with more radiation shielding, but that means it's more massive, which means you need to have more propulsion, more propellant, and that's an economic problem. But as we develop the cislunar economy and get infrastructure in space, the economics is going to be changing. And then faster travel time, that can be done with new propulsion systems, which NASA has been funding development of steadily. So I think, yeah, going farther with our biological bodies in space is a challenge, but I do think these are the kind of challenges that we can overcome through technology.
Hi. So we've been talking a lot about like using the moon as a resource, both for commercial and scientific purposes. And I wanted to ask if you could talk a little bit more about how are we going to make sure that we like don't run out of the moon as a resource and how we like don't overuse it.
So that's a really good question, and especially in LSIC that comes up a lot because we don't have the best track record as humans in managing our resources. And one of the things we talk about a lot is how do we plan now to have our economy be as circular as possible, right? So that if we extract something, every waste product we create, but whether we're trying to basically like crack oxygen out of rocks to produce the free oxygen, the metals we produce, how do we make sure we use those? How do we make sure that we repurpose things that we've brought ourselves? So, I think there's a lot of discussions going on about that to be good stewards of the moon, because especially when you look at it internationally, the moon it's been our partner for all of human history, right? And like people look up at it in the night sky, we love it for different reasons. We don't want to be proceeding disrespectfully and just like, we think about strip mining. Like, I think that's kind of the ugly vision that comes to mind a lot. But, we want to have the discussions and understand how we can, get the scientific information that we need, but be as careful and as what's the opposite of wasteful? I don't know. Not be wasteful in what we're doing. Really be mindful about how that we're proceeding with this. So, I guess what I would say is that, we would be using some element of things, but we're really trying to understand how to minimize that environmental impact on the moon as a whole.
Yeah, and I think I think that a lot of the people who are working on space resources are aware that the lunar volatiles are a non-renewable resource over timescales equivalent to the age of the sun. So it is a non-renewable resource, and so a lot of people are thinking, as quickly as possible, we want to move on to using asteroids, but that's a little farther out. That you got to do the things closer to home before you can do the things a little farther out. But the resources from asteroids are, orders of magnitude more than what we would have from the moon. But a friend of mine, Martin Elvis, who's an astrophysicist at the Harvard-Smithsonian Institute, he and some others co-authored a paper recently where they argued that within a reasonably short amount of time, we could end up depleting solar system resources if industry and economics grow exponentially. And so they were already proposing having limits, setting aside a certain fraction of the solar system as park space, to preserve it. So we do need to be looking forward in that direction at all times. And I agree, those are important questions.
We're going to get hooked. I think we're going to get the hook.
The remaining questions can be very quick questions with very quick answers. So we'll go to that one first.
Thank you for the wonderful discussion. My question, you mentioned them slightly about small sats, CubeSats. I know of you, especially you mentioned the simplex, but given the volume of launch opportunities to Earth escape, is there going to be funding available for, sub $15 million, sub $5 million that can make, 12 and 6U CubeSats that could do, not important science, but collectively, if you have 20 of them, 30 of them, 100 of them over a launch campaign, is there going to be, funding for that profile of a mission, and kind of maybe even, and then the acceptance of them being high risk and a third of them failing, but you're going to launch 100 of them, to do lunar science?
I guess what I'll say to that is that we're always going to be moving in the direction of trying to get good science out of the smallest size, smallest mass instruments and vehicles that we can. I can't address the specifics of your question. I would say ask your congressman.
Yeah.
And one more very quick question. Okay.
So the question is about using different kinds of propulsion, getting humans out to the moon and other celestial bodies faster.
There's a lot of wild ideas out there, and some of them already have some development done. But one idea using just electric propulsion with higher thrust, it's very efficient for propellant, and therefore you can burn your engines the whole mission, and it can actually make a mission be faster if you have enough thrust into it that way. There are others working on something called the Vasimir, which is an electrodynamic process to use plasma to get higher efficiency thrust. Nuclear propulsion, where you're using a fission reactor to create heat to drive a thermodynamic cycle like a Brayton cycle to convert it to electricity. There's other direct nuclear thrust where you just simply use the heat to directly heat hydrogen, so you don't combust the hydrogen, and it's more efficient if you don't combust it because lighter propellant molecules give you higher specific impulse. So there's a lot of ideas out there. One part of NASA that funds this work is the NASA Innovative Advanced Concepts program, NIAC. And there's also been crazy ideas like putting a particle beam on the moon and using it to push something like a solar sail so that you could actually go interstellar over a reasonably short amount of time. So there's a lot of ideas out there. Some are far in the future, but some are pretty close to implementation.
Well, thank you all for participating in the panel this afternoon. I hope you've been able to pick up on why we're all excited about the year coming up. When you get to the end of 2023, look back and you're going to see all the different lunar missions that took place in 2023 and what we learned about them worldwide. Thanks, everybody.